I was going to talk about the kind of synergy that that the nuclear astrophysics has with gamma ray astronomy. And funnily enough, this week also had the meeting for the Amigo science team. So I was giving essentially the same talk, but from the opposite point of view, just this Monday. So hopefully I can not confuse you all with the gamma ray community when I give this talk. The thing that's, I think, exciting right now is that there is a big push right now to do the next level, gamma ray astronomy. There are lots of missions being proposed: Ascent, COSY, LOX, Amigo, and I just have a picture here on the right of the COSY mission and also the sensitivity curve for Amigo and Amigo X, which is being proposed in the next round. What is happening is, especially in the MeV range, we're going to get at least about an order of magnitude better sensitivity, and that means we can look at a lot more. We might have advantages to study some of the gamma ray, nuclear decay gamma rays coming out of different astrophysical sources. So I think they have a lot of interest in what they can do for nuclear astrophysics, and I think it's a good time to bring the two communities together. We've had a lot of discussions of this, but where there are where there's some can be done. There's core collapse supernova, there's thermonuclear supernova, and here I show gamma rays from the cobalt 56 decay that was observed in a nearby type 1a supernova. And the feature there was that the type 1a supernova, by looking at that gamma ray decay, you can actually learn about the morphology and the explosion mechanism of the type 1a supernova. So people have studied that in detail, and there's a lot of focus on that. But I think there's a lot of other interesting nuclear physics with nova, X-ray bursts, common envelope evolution. So I think there's a lot of science that we can be doing if we can communicate to the gamma ray astronomy community what are the needs for these different detections. So 1A's one of the big things is nickel 56, which I think not as interesting in the nuclear physics side because I think we know what's going on there. But in other supernova like core collapse, titanium is important. We've done studies of what are the magnitudes of different decay lines for different supernova explosions, and you can get a much broader set of isotopes that would be interesting if we had a nearby core collapse supernova and could study the nuclear yields using gamma rays. And I just show some plots from Wangwathanarat did a study. This is, I think, the titanium distribution from one of their asymmetric supernova explosions. And then there's earlier plots by Hungerford et al., and then a total yield plot by Sidney Andrews. So there's a lot of science we could be doing in core collapse supernova. The classic one was looking at titanium and looking at the different titanium yields. This was done by Maklotzius et al. These plots are looking at peak temperatures and densities and then asking what's the nickel 56 yield on the left, what's the titanium 44 yield on the right. And you can see how, and then the different colored dots, triangles, are different supernova explosions and where they lie on that peak temperature, peak density regime. So typically you can look at the yields, you get a peak temperature density, and then they decay. And you can ask the question of how well can you probe yields from these gamma rays or conditions from the gamma ray emission from these two tracers. And you can see that whereas you can get a good idea of the conditions with the nickel 56, the titanium is really a strong discriminator on the exact conditions of the explosion. And we have used this to look at things like the titanium 44 in the Cassiopeia A supernova remnant. Here the silicon is colored in green, the iron is colored in red, and the titanium 44 is colored in the cyan color. And I will tell you that this is probably the most direct evidence that the kind of convective supernova engine that Evan O'Connor talked about earlier is really the right engine for at least this particular supernova remnant. And I suspect it's the right engine for a majority of the normal supernova that we observe. And so this has really done a lot for the science. But if you're talking about nuclear physics, we want to figure out how can we look at this data and learn, either improve it with better nuclear physics, or learn something about nuclear physics from this data. And that's what we would want to provide to the kind of the gamma ray community. The other kind of isotopes that people look at often are aluminum-26 and iron-60, and there's been a lot of new studies on that. I'm showing on the right here some of the interests that the gamma ray community had in this science based on the gamma ray paper that was a white paper that Frank Timmons and I led a year ago to help give justification to the decadal review for astronomy to build a gamma ray instrument. Since this time, there's been increased work on things like iron-60 and where could it be produced. I think studying the rates will make a big difference here. So if we can really build that case, the gamma ray community is very interested in doing these studies. They do it to study things like star formation in the Milky Way. So it's one of the strong probes for star formation in the Milky Way. You can look at how does it differ between that and where the gas lies now. Roland Deal and collaborators have a lot of work on that. So I think there's, astronomers are realizing that these are really useful tools. I think what they don't realize as well is there is the uncertainty in what happens if I play with the nuclear rates. There's nuclear rate uncertainties that need to be studied when they're doing this science. And the last slide here in the middle is a image of a kilonova remnant. So this is what happens when you have two neutron star mergers. And we already had a lot of discussion on this. Was it yesterday or the day before? But by both Jennifer Barnes, Rebecca Sermon, where you can, these mergers are believed to produce a lot of heavy R process elements. And the interesting feature there is it's hard to see them. If you're going to say, I'm going to see it from a gravitational wave detection, it's going to take a nearby event to see anything. But there could be an old old kilonova remnant in the Milky Way. And it turns out even 10 kiloyears after, so 10,000 years after a kilonova, they're still bright because of these intense broad set of yields. They're still broad and bright in the between 100 and a couple MeV, where a lot of these gamma ray detectors are going to be sensitive. And there could be if we're lucky, there might be a nearby old remnant that we could observe in the gamma rays. And then we can really probe what's happening with the nuclear physics. Because I think we'll start seeing what are the exact yields. And there's lots of uncertainties there in both what is the explosions and the ejecta properties of these kilonova, but also in the nuclear rates. And I think Rebecca covered some of that. So I just wanted to end with how do we make these ties better? How do we make a better connection to the gamma ray community? As I already mentioned, there was a white paper called Catching Element Formation in the Act. It kind of focused on what can we observe with the gamma rays. I think one of the things that the gamma ray community needs now more is, can we identify interesting isotopes produced in transients? We need to get good trajectory sets where we can study them and produce, say, look, can you go see these? Tell the satellite developers, can you go observe these isotopes? What resolution can you observe these isotopes? So I think there is some work that still needs to be done to really clean up that picture. And then so that's just what are interesting isotopes that we can produce in the transients. The other is there anything where they can do nuclear physics by doing better observations? And the kilonova is a classic example. You can vary how you do the nuclear physics, a variety of processes, including isomeric states. And you can then ask the question, does it produce a different signal? And then ask the gamma ray observers, can you go observe this signal? So I think there's some science to be done to make those ties better. And that's what I would like to have discussions on with this group.